Java, C#, Golang all has a garbage collector, and Python also has automatic garbage collection. But C++ does not. So the question is, without a garbage collector, are C++ programmers manually managing memory every day? Many people would say yes. But in fact, this is precisely one of the biggest misunderstandings about modern C++. To explain this clearly, let's first look at what a garbage collector actually does. Suppose you create an object. As the program runs, more and more objects are created. Among them, some objects are no longer pointed to by any variable. These objects will never be used again in the future. The job of the garbage collector is to find these objects and then automatically release the memory they occupy. The programmer hardly needs to participate in the whole process. Sounds perfect, doesn't it? So why doesn't C++ simply adopt this approach? Because the garbage collector is not free. Whether it's reference counting in Python, Perl, Mark, Sweep, in Java, C#, or other more advanced algorithms, in order to know which objects are still usable, it needs to continuously scan memory and trace the reference relationships between objects. Some garbage collectors even need to pause the program to perform collection in a concentrated manner. This is what many people have heard of: stop the world. The JVM operates in this way. Although modern garbage collectors have improved a lot and the pause times are getting shorter, for game engines, databases, browsers, operating systems, or high-frequency trading systems, any unpredictable pause can cause performance issues. Therefore, C++ chose a different path from the very beginning. First, C++ has a finer division of memory. The vast majority of local objects live on the stack. Stack memory allocation is just a single CPU instruction, several orders of magnitude faster than heap allocation. Moreover, objects on the stack are destroyed along with the function stack frame, releasing memory immediately, completely, and with zero latency. There's no need for a garbage collector at all. If an object is too large, or needs to survive across function calls, it goes to the heap. At that point, C++ still has a trump card. The core idea of modern C++ is called RAII, which stands for Resource Acquisition is Initialization. The name sounds complicated, but the idea is actually very simple. Resources belong to objects, and C++ guarantees that when an object goes out of scope, its destructor will be executed, unless you deliberately turn off exception handling. This mechanism is absolute and deterministic, unlike Java's finalize, which you never know when it will be called. Now look at the following code. Have you noticed? We almost never use the delete keyword. Why is that? Because when numbers goes out of scope, its destructor is automatically invoked. The allocated memory is also automatically freed. At this point, some might ask, since RAII is so powerful, why does C++ still keep new and delete keyword? The answer is simple, because someone still has to allocate resources. For example, in the following two pieces of code, although heap memory is still being used, the resources have already been handed over to the object for management. When the object is destroyed, the resources are automatically released along with it. Now let me ask a question. Vector can help manage an array, but what if you only want to manage a single object in the code? What should you do in that case? The C++11 standard library introduced 3 smart pointers, completely ending the era of manually writing delete. Unique pointer. Zero overhead. It is the same size and as fast as a raw pointer. It has only one requirement. The memory is owned exclusively by me. No copying is allowed, only moving. When you move a unique pointer to someone else, you become empty. When it goes out of scope, it directly calls delete. This is the most commonly used pointer in C++, because the vast majority of objects have a clear single owner. Shared pointer. The reference count is shared on the heap. When the last shared pointer disappears, the object is destroyed. Does this sound like Python's GC? No. C++'s reference counting is deterministic. The destructor is called immediately the moment the count reaches 0, without waiting for a background thread to scan. The performance overhead only occurs during copy construction. Weak pointer. Specifically designed to break cyclic references with share pointer. It does not increase the reference count, and only temporarily promotes itself to a shared pointer when needed to access the object. Modern C++ also introduces move semantics. It does not copy memory. It only steals ownership of the resource. Compared to traditional C++ deep copying, it is extremely fast. For example, in this piece of code, the receiver directly takes over the internal pointer of local, and local itself becomes an empty shell. This process does not allocate new heap memory, does not copy data, and there is absolutely no need for GC involvement. This is a unique performance advantage of C++. Many people think that the opposite of a garbage collector is the programmer manually writing delete. This is a misconception. The garbage collector determines at runtime which objects are no longer in use. But C++ trusts the entire lifecycle of an object, including creation, resource acquisition, destruction, and resource release, to be the object's own responsibility. So for C++, resources should follow objects rather than the programmer.